In the last lesson, we learned about simple proportions, which are when two ratios are equal. In this lesson, we're going to learn about when large sets of ratios remain equal. Let's start with one that you could hold constant, and that is speed. Speed we all know of as distance per time. Now, if you were in a race car going around a track, this track is 1 mile around, you could try to hold the speed constant as fast as you could go. In that case, you might go the first 15 laps in 6 minutes, or 0.1 hours, and the first 30 laps in 12 minutes, or 0.2 hours. Has your speed remained the same? Has the distance per time ratio remained the same? Well, the distance has increased by a factor of 2, and the time has increased by a factor of 2. So yes, those ratios are equivalent. How about if you go the first 75 laps in 30 minutes, or 0.5 hours? Let's do the same logic. The distance has increased by 2.5, and so has the time. So your speed has remained the same again. So say you're going this speed, how far are you going to go in an hour? Well, that means the time is going to have to increase by 2 from our last measurement. So we want to increase the distance by 2. And that means we'll have 150 laps in 1 hour. And we know a lap is a mile, so the car's going 150 miles per hour. And that ratio, just to reiterate, is the same as our 15 over 0.1 hours, 30 miles per 0.2 hours, or 75 miles per 0.5 hours. So here, the race driver has held his speed constant. Now let's check out this cool thing that happens when we graph the race car's speed. So we know that speed is the distance the race car travels over time. So let's put distance along the y-axis over time along the x-axis. Our first data point is going to be at the origin because the car traveled 0 miles in 0 hours. So let's plot that. All right, and then you remember our first distance was 15 miles in 0.1 hours. And then the car traveled 30 miles, or 30 laps, in 0.2 hours. The next data point we had was 75 miles in 0.5 hours. And finally, we figured out that if the speed were the same, the car would travel 150 miles in 1 hour. If you'll notice, these points fall along a perfectly straight line through the origin. And that's because our speed remained constant, the ratio of distance over time. Now let's consider the slope of this line, which is the rise over the run. And you'll recognize, in our case, that's distance over time. So it should be our speed. Let's check it out. So here is an arbitrary rise over run along this line. It's 60 miles up and 0.4 hours over. Well, 60 miles divided by 0.4 hours does indeed give us 150 miles per hour. And it turns out that a straight line through the origin on a coordinate plane indicates a proportional relationship because the slope is equal everywhere. The slope being equal means that the ratio of rise over run is equal everywhere. And you know that equal ratios means a proportion. That's why we call it a proportional relationship. But speed is only constant some of the time. Of course, when a car first starts up, it has to increase its speed. When it goes around a turn, it typically slows down slightly. So the only time we'd have a constant ratio of distance over time is when the driver holds the speed constant or sets it on cruise control. But there are some instances in nature where the ratio would never ever change. And that's what we're going to look at now. We call these special cases constants of proportionality because, well, proportionality means equal ratios, and constants are things that never change. So these constants of proportionality are equal ratios that never change. And one of our favorites is pi. Pi is defined as the circumference of a circle divided by its diameter. No matter what circle you have, this is always an equal ratio. Let's see if we can convince ourselves that that's actually true. Here we have the circumference of a circle in blue, and now the diameter in red. We want to find out what is the ratio of the circumference to the diameter. Or in other words, how many times would the diameter fit in the circumference? Let's start by opening up the circumference into a straight line. Then we can copy the diameter however many times we need to reach the end of the line. We find that the diameter fits along the length of the circumference a little more than 3 times. And if you measured it carefully, you'd see that it was 3.14 times. So here we found that the ratio of circumference to diameter is approximately equal to 3.14. Okay, let's look at a much bigger circle. Here, we have another circle with a diameter through the middle, and we're going to open up the circle's circumference and line up the diameters along it. Again, you get the same result of slightly more than 3 diameters inside the circumference. So again, C over D is approximately equal to 3.14, even though we have a completely different circle. Let's look at some circles we could measure. On this car, the wheel has a circumference of 179 centimeters, and the diameter measures at 57 centimeters. So if we take the ratio of circumference over diameter here, we get 3.14. Let's look at the smaller circle of the headlight. This circumference is 69 centimeters, and its diameter 22 centimeters. Dividing those, we get 3.14. So this ratio of circumference to diameter seems to be constantly equal. And so that's why we call the quotient a constant of proportion. C over D equals the constant pi, and that's approximately equal to 3.14. But pi is not the only constant of proportion. Let's take a look at what Lavoisier found when he was studying how water broke down into oxygen and hydrogen. He saw that the water he put through the hot iron pipe converted into some oxygen that added to the weight of the pipe, and some hydrogen as a gas. Let's look at the measurements that he made of these different masses: the water lost, the pipe gained, and the flammable gas that was released. In one test, he might have found that 18 grams of water was lost, the pipe gained 16, and there were 2 grams of hydrogen. In another, he might have noticed that 54 grams of water was lost, 48 grams of mass was gained by the pipe, and 6 grams of hydrogen were collected. Finally, 90 grams of water was lost in one case, with 80 grams of oxygen being gained in the pipe and 10 grams of hydrogen being collected. In all of these cases, you'll see that conservation of mass holds. The mass of the water lost was equal to the sum of the mass gained by the pipe and the gas. But something else is interesting here, and that's the ratio of oxygen to hydrogen. Let's calculate those ratios. So the ratio of 16 grams of oxygen per 2 grams of hydrogen gives 8. And 48 grams of oxygen per 6 grams of hydrogen also gives 8. 80 grams of oxygen per 10 grams of hydrogen, again 8. So Lavoisier noticed that when he divided the mass of water that became oxygen in rust by the mass of water that became hydrogen as a gas, the result was a constant. So he concluded that in water, the ratio of oxygen to hydrogen is fixed. It is a constant of proportion. In the next lesson, we're going to look at more cases of constants of proportionality that early chemists discovered.